This is part 3 of explaining the June 2023 skeleton code. In this video we'll cover execution, which is the last input we need to cover. The code in this video will be more difficult than the previous videos, so pay extra attention. I advise you to read at least the first 4 pages of the preliminary material document. It will be attached in the description. When we run R, we first check the operand value of the first index in memory. This is because if the value is anything less than 1, there must have been an error. The first operand is always jump, and the operand value is either the line where the start label occurs or the first line of code. To populate memory, we need to run assemble, and to run assemble, we need to load the assembly program. Essentially, this if statement checks whether or not we have loaded a file. The second check looks for if there's been an error while assembling the file. These error flags are spread all around the code wherever there's been a critical failure in assembling the file into memory. What this means is that the code won't run if the program can't correctly assemble the file we provided. If the program has been assembled and has no errors, we can start executing. Before we talk about executing, we need to discuss the status register. The status register is 3 characters long, and each character represents an outcome of an operation. The characters are in order Z and V. Z represents a 0 being the outcome of an operation, N represents a negative number being the outcome of an operation, and V represents an overflow error. An overflow error occurs when a number cannot be represented by 8-bit binary. This is when the number is bigger than 127 or smaller than minus 128. There's a notable exception to these rules, however. In compare, the Z and N flags serve a different purpose. If the contents of the accumulator are equal to the operand in compare, Z is set to 1. If the contents of the accumulator is less than the operand value, N is set to 1. If the contents of the accumulator is more than the operand value, N and Z are both set to 0. We decide all this with the setFlag subprogram. Here we can see exactly what I explained. If the value is equal to 0, Z is 1. If the value is below 0, N is 1. If the value is unable to be represented by 8-bit binary, V is 1. Leaving, if the value is greater than 0 and is not an overflow error, all flags are set to 0. Another important concept you need to be comfortable with is the concept of stacks. In the preliminary material, stacks are described as so. A stack is used to store the return address when a subroutine is called. In the simulator, the stack is built downwards from the highest memory location. The TOS register stores the address of the most recent return address pushed onto the stack. Before a return address is stored on the stack, the TOS is decremented by 1. After a return address is retrieved from the stack, the TOS is incremented by 1. That's a lot of words all at once. For now, we don't need to go over stacks in extreme detail, but here's what the examiner means. The only time a stack is utilized is in the return command and the jump subroutine command. The best place to see these in action is in Prog3. Prog3 tests multiple subroutines inside subroutines, so it's crucial for stacks to work properly there. However, Prog3 also performs some extra calculations, so as to not muddy the water, I've made my own assembly program to test this, Prog4. Prog4's only job is to test stacks, so it only uses the return and jump subroutine commands. When we start the program, our first instruction is to jump to line 10, which is where start is. This is normal and occurs on every program. If there's no start label, it jumps to line 1. At this point, the PC register is now 10. Before the next command's execution, the PC becomes 11. We then set the stack, which is the line number to return to 11. The reason the return value or stack is 11 and not 10 is because we don't want to return to line 10 and repeat the JSR command. That's why you return to the line preceding the JSR call. This process repeats for all JSR calls until a return call is met. Return works just like JSR but backwards. It grabs the most recent stack, or the top of the stack, which is stored in the TOS register. It then sets the PC to the line number of the stack. This means it will start executing from that PC count onwards, which means it will start executing from that line onwards. Funnily enough, the PC register matches the code's line number, so what that means is that if it helps you understand jumping between lines, you can imagine the PC as the line number to jump to. That's the status register and stacks explained, at least to a rudimentary level. Now we can start looking at executing the assembly code. As you can tell, there are many subroutines involved in performing each command, so I won't go over all of them. The simpler ones like add and sub you can probably get away with knowing just the preliminary material info on them and then having a cursory look at their code. I will be explaining compare, break if equal to, jump subroutine, return, and I'll explain how this program handles immediate addressing. But first, let's start with the execute subprogram. First we create an integer array called registers. This is where all our constants come into play, as each constant corresponds to an index location in registers. TOS is 3, so writing registers TOS is the same as writing registers 3. The constants are simply there to make the code more readable. It's easier to know what registers PC refers to than registers 0. After that, we use a subprogram setFlag with the contents of the accumulator register. All this does is set the flag Z to 1, making status 100. Register's PC is set to 0, though doing this is unnecessary as it's already 0. It may have been done to make the code more understandable. Then we set top of stack to 20. This just means the stack will start on line 19 in memory. More on that later when we cover the return and jump subroutine command. The next 3 lines just display useful information like the frame number, the memory variable, the source code, and the registers. Finally, we grab the first instruction or opcode in memory. This will always be jump, and it will either be to line 1 or to the line where the start labeler begins. Now we initiate the main execution loop. Whilst the program doesn't encounter the halt opcode, it will continue to run the code. Right at the start of the loop, we display the frame number. At this point, its frame is 1. Then we grab the operand value of the current instruction and store it in operand. Since we have both the opcode and operand, we display the current instruction at hand. For prog 3, this would be jump 12. Now we increment PC by 1 in anticipation for our next command. This next section is where we start executing the commands, but we'll cover this later. At the end of every command, we check for errors. If there's been no error, we grab the next instruction or opcode and display information like the memory, source code, and the value of the different registers. If there's been an error, opcode will become halt. Because this is right at the end of the loop, it means that we effectively stop executing by no longer meeting the while loop's condition. In that case, we simply notify the user that execution is finished or terminated, and that's the end of the execution subprogram. Now we can start talking about how some of the opcodes actually function. A lot of them are very simple, like skip, jump, add, etc., but some of these are a bit more complex than others. We start with the easiest commands and slowly progress to the harder ones. First, we'll take a look at compare. Weirdly, this command only has an immediate addressing mode, so we'll also cover making a new compare command with a direct addressing mode. Pay extra attention to that section, as the absence of this command seems so unlikely it's probable it was on purpose. Maybe it's for an exam question worth 3 or 4 marks. The compare command compares the value in the accumulator with the operand. It then sets the register flag accordingly. It sets Z to 1 when the accumulator matches the operand value, N to 1 when the value in the accumulator is less than the operand value, and if the accumulator is greater than the operand, Z and N is 0. The reason V is never changed is because V is only changed when there's an overflow error. This is how it looks like in code. First we create a variable called value. We assign value the difference of the accumulator and the operand. What this means is that if the accumulator and operand are equally matched, the value variable will be 0, meaning Z will be 1. If the accumulator is less than the operand, the value variable will be negative, making N 1, leaving if the accumulator is greater than the operand, the value will be positive and greater than 0, making both Z and N 0. Now to make this command have a direct addressing mode, if you remember, a direct addressing mode means the operand is an address pointing to a value, and an immediate addressing mode is when an operand is the value. All we need to do is change the operand parameter name to address for the sake of the code being more readable. Then we change the first line from having minus operand to minus memory brackets address dot operand value. And it's as easy as that. Remember to add compare in the opcode values string array inside extract opcode subroutine, otherwise the program won't recognize the command. The next command is BEQ or break if equal. What this command does is jump to the address specified in the operand if the status register has Z equal to 1. First we create a string variable called status register and store the binary result of the status register's number. This is because the status register holds the denary equivalent of the 3-bit status flag we are used to. Z being 1 is 100, making the status constant 4, N being 1 is 010, making status 2, and V being 1 is 001, making status 1. After we create the status register variable, we create another variable called flag Z, which only takes in the first character of the status register flag. Once again, this process can be improved by just not grabbing the whole status register and only grabbing the first character of the status register in one line, like so. When implicitly converting a string to a char, it automatically grabs the first character of the string to become a char. Of course, we could specify which character to grab as well, but it would add more brackets and it's already getting a bit cluttered here. Then we set the PC register to the address we specified in the operand. This code should be familiar as it's exactly the same as the code in jump. However, the jump only occurs if Z is 1. If not, nothing will happen. Now finally to jump subroutine and return. These will be in one section as they're both very similar to each other. We start with jump subroutine. We start by grabbing the TOS register -1 and store it in the stack pointer. If it's our first time executing this, our stack pointer will be 19. Then on the second time it will be 18, 17, then 16, etc. These are all index locations in memory. As you can see on the second line, we assign to the operand value structure under memory at stack pointer the value of the PT register, which is the line number to return to. In prog 3, the first stack would be 14. That's because the JSR call is on line 13. We then perform the jump on the next line. Now we update the TOS register to the stack pointer, so that the next time we run this command, we grab the next available stack location. That would be 18. Finally, we display the stack to the user. This subroutine is quite simple, so you can check it out yourself. Now we can talk about return. First we grab the current/most recent stack pointer. This will match up with the current value of the TOS register. Then we add 1 to the TOS register in preparation for the next time we need to return to a stack. Finally, we set the PC to the operand value structure of memory at the stack pointer. This effectively moves the path of execution because, if you remember, the PC lines up with the line numbers of the assembly program. These two commands are quite complex in comparison to the others, so make sure to rewatch this section of the video and debug the program until you understand them. However, there is an issue with stacks. The perceptive programmer will realize that if the program is long enough with enough JSR calls, it will start overwriting operand values that are in use. In Prog 3 we test subroutines. First we load 7 into the accumulator and add 7 4 more times to the accumulator. After that we store it in num2. That should leave us with 35 in the accumulator, but it doesn't, it leaves 37. Stacks are the culprit. When we assemble the program, we take up 17 spaces in memory and source code because the program is 17 lines long. Line 16 is a label pointing to an immediate value of 7. It's crucial for the program to have this value constant. Let's dry run the program and observe the end of memory, which is where the stacks are placed. The first time we have a JSR call, the end of the memory array, index 19, is updated to have an operand value of 14. Next JSR call, index 18 of memory has an operand value of 3. Next call, operand value of 6, and so on. We have already interfered with the assembly program. The operand value of index 17 of memory should be 0 and always 0. This is because index 17 is reserved for num2 in the assembly program. Next JSR call falls on index 16 of memory and changes the operand value to 9. This happens right before the final time we add num1 to the accumulator, which is supposed to be 7. That means we add 2 more than we need to, and the result in the accumulator is 37, not 35. There are multiple ways to fix this, but the easiest and fastest way to do it is to create a new field in the assembler instructions structure. We call this field stack pointer value and make it an integer. Now all we need to do is change all instances of memory.operand value to memory.stackPointer value inside jump subroutine and return. Not only does this resolve the interference between the stacks and assembly code, but it also means we can have more calls and more assembly code in our program. We have finally covered all major aspects of the program. There are some subprograms we haven't covered yet, and that is some display subprograms and some execution subprograms, but those you can cover yourself. I'll also have a GitHub link to a fully commented version of the code. You can use this to aid your studies. This was the last part of this series. Thanks for watching.